Hello and welcome to our discussion of weather radars. And in this video we're going to talk about the different types of radars. Here's the list of radars that we're going to discuss. We're going to start out with air traffic control radars. Air traffic control radars operate in the S or L band, typically the L band. And they're usually 20 centimeter radars, which are long wavelengths. These are used by air traffic control across the United States to look for aircraft. Aircraft are large objects in the atmosphere, so that's why they use a long wavelength. Different types of radars that are used across the United States. Typically near airports they have airport surveillance radars, or ASRs, and those are currently in the 9th generation, or ASR 9s. You can see that these have very large antennas because you have a very big wavelength, very long wavelength. Also, air traffic control radars are scattered across the United States looking at the atmosphere, looking for aircraft over large distances, and these are typically the ARSR radars that are used by air traffic control route centers to look for airplanes in their airspace. Another type of radar that's used is a ground-based weather radar. These are typically either 10 or 5 centimeter radars. The National Weather Service has a network of 10 centimeter radars. It's called the WSR-88Ds. These are Doppler radars, and they're located all across the United States to detect precipitation and also looking at radial velocities to try and figure out if there's tornadoes or microbursts or other things. And then the FAA has a C-band type radar that's located near airports. It's called TDWR. TDWR stands for Terminal Doppler Weather Radar. These are radars, 5 centimeter radars, so they can see smaller objects in the atmosphere, small drops, and even aerosols in the atmosphere, and they can even pick up clear air returns sometimes. And TDWRs are usually about 10 miles to 15 miles from an airport. They scan over the airport looking for wind shear and microbursts. Airborne weather radars are typically carried aloft by airplanes. Usually the antennas in the nose of the airplane. Since the antennas are very small, you need a smaller wavelength, and specifically they use 3 centimeter radars. If it's a very large airplane and if the airline wants a different type of radar, sometimes they use a C-band. The advantage of C-band is that they do not attenuate as much as X-band radars. So that's a big plus. However, remember that longer wavelengths mean bigger antennas. So a C-band radar usually can only be carried in the largest aircraft. The antennas are very big. Another type of radar is the satellite-based radar. These are Ku band radars, shorter wavelengths. Typically, of course, on satellites. One recent satellite that went up was the Tropical Rainfall Measuring Mission. And that satellite scanning down on the Earth, taking swaths of measurements across clouds to figure out how much precipitation is in these clouds. And that's done with a Ku band radar, shorter wavelength. And then finally, smallest wavelengths are looking at very small particles in the atmosphere. Cloud droplets are typically very small, anywhere from 5 to 20 microns in size. So they use the shortest wavelengths, 0.75 to 2.5 centimeter wavelengths. And an example of this is the NOAA millimeter cloud radar. There are a few of these scattered across the United States at field sites that are doing climate research. And they're looking at cloud structures as clouds move over. It's a vertically pointing radar. There are other types of radars. Another example is the Doppler, or sometimes called coherent radar. This is a radar that's able to measure the Doppler shift. Doppler shift is where you get a change in the frequency of a signal that was transmitted. So it goes out at a particular frequency, and then it comes back at a different frequency, or you could say a different wavelength. And the reason for that is because there is a speed difference between the transmitter and the target. In other words, either the transmitter is moving or the target is moving. Since most weather radars are fixed on the ground, then it's typically the target that is moving. So Doppler radars will detect the change in frequency. If the target is moving away from the radar, it'll measure a radial velocity, and the wavelength that comes back will be longer in an increased wavelength or decreased frequency. And conversely, if the targets are moving towards the radar, then the frequency coming back will be greater, or in other words, you'll have a decreased wavelength in that signal. So once again, this only measures the radial velocity, whether it's coming towards or away from the radar. Many times, targets are not moving directly towards or away, they're moving at an angle. So the Doppler radar only measures the radial velocity, and as a result, you don't know what the actual velocity nor the tangential velocity. You just know whether it was moving towards or away from the radar. Another type of radar that has been deployed across the United States with the National Weather Service radars is dual polarization. All the WSR 88Ds have been upgraded to dual polarization approximately 8 years ago. And dual polarization means that it can send out a signal that is polarized in both the horizontal and also the vertical planes. So here this picture shows a signal going out that is horizontally polarized, and the bottom picture shows one that is sending out a signal both in the horizontal and also the vertical. So the beauty of this is that you can detect different things or different scattering, backscattering, with either the horizontal or the vertical. So in other words, the amount of radar energy coming back in the vertical may be different than the amount of energy coming back in the horizontal. And the difference in that reflectivity is a function of the shape of the target. If the target is birds or bats, then they reflect radar energy kind of differently in either plane. However, if it's perfectly round, a sphere, then it'll send back backscatter energy approximately the same intensities both in the horizontal and the vertical planes. So the difference in reflectivity, the differential reflectivity, will help you determine what type of target is in the atmosphere. Another type of radar that's just in the planning stages right now is phased array radars. The typical National Weather Service radar rotates kind of like the way you see right there, where it's scanning the atmosphere by rotating the antenna, and of course the antenna is driven by a motor and servos, so it scans the sky. Typically it takes anywhere from 5 to 7 minutes to scan the entire atmosphere, sometimes maybe a little bit longer. But phased array antennas, instead of rotating, what they do is they scan the sky by changing the charge pattern to the antenna array, and as a result the angle can change almost instantaneously just by charging the radar antenna at a different timing. So it can scan the atmosphere very quickly, much more quickly than your typical National Weather Service radar. It only takes up to 30 seconds to get a full volume scan. WSR 88D radars right now scan the atmosphere. It takes about 5 to 7 minutes. Also, you can go back and take a look at areas where you have perhaps an interest or something that's drawn your attention. For example, if you're looking at a mesocyclone developing in a thunderstorm, you could actually scan it many times quickly and see it develop and get a warning out a little bit faster. The other advantage of phased array radars is that there's no motors, no servos, so there's a much lower failure rate than with the current National Weather Service radars. So those are the different types of radars.